So, hi, my name is Firat. I work for Pagoda, which is part of NEAR ecosystem. We're the core contributor to NEAR protocol. And today, I'm going to talk a little bit about data availability and what we're doing at NEAR protocol for data availability layer for Ethereum rollups. Did anybody until now talk about data availability at all, or is this the first time that this crowd is hearing about it? First time? Okay, that's cool. And rollups probably way in detail, right? Like everybody just kept going. Okay. Well, to understand what we're trying to do, we kind of need to understand what data availability is in the context that we're in, right? It is actually very basic when you think about it, but it's a principle that data that is stored on a network is accessible by and retrievable by all network participants. And that's literally it. That's all. The problem is when you try to do this in scale. We heard about a lot of scalability solutions. But what is the problem with scalability? Obviously throughput, right? Like if you do it naively, if you try to do it with a lot of participants in a decentralized manner, you run into the problem that not everybody will be able to download all the data. It just doesn't really scale. But the data availability problem still is there. If you want to provide the data to everybody and make it available for everyone, the network still needs to guarantee that all block data is available to all participants. Okay, so how do we do that? Well, let's talk about a little bit first around how scalability is achieved in different ways. We're NEAR protocol, we're in L1, right? We're trying to do scaling in a different way than rollups at the moment. We're trying to do it on chain. It's sharding, that's what we call it. We're trying to do dynamic sharding. Ilya is here, Bowen is here. They would have more data on it if you guys want to ask later on. But what we're trying to do is we try to keep all of the layers of a blockchain monolithic in one place. And then we're trying to shard the execution and the data layer, basically. And this is going quite well. We have some developments. On the Ethereum side, I think after 2019, I'm not sure about the exact date, but new off-chain scaling solutions came into play, right? There's Plasma, which I read a paper yesterday that was explaining that it might come back. But the real what generally the ecosystem is working on right now is the rollups. What does rollups do? They take the execution layer out, do off-chain execution, and sometimes they take the data availability out from the L1 and then put it somewhere else. But let's say we take the execution layer out and then we do some execution and then we want to put it back to the L1 as the settlement. How do we know that the state transition that we did off-chain based on the transactions that we executed are correct, right? So I'll just skim this through because everybody knows about this. There's two ways right now that is kind of the canonical way of doing this. One of them is optimistically, you just keep going until somebody says, hey, there's a fraud and you shouldn't do this anymore, and provide a fraud proof. And then you do it on the L1, the settlement on L1. You say, okay, I'll do all these transactions on state A to go to state B. And if there's a fraud, we roll back on the L2. The other one is GK rollups. I call it cryptography magic because I'm not really well versed in it. But at the end of the day, what you do is for every transaction execution that you're doing, you provide availability proof. And then what you do is you put the state diffs if it's ZK sync or transactions for other one. You keep it on the data availability layer. Why is DA even a thing for rollups, right? Just like I said, how do you trustlessly verify the correctness of computations performed off-chain? I can just put anything on L1, and if nobody's checking it, I can just make them pass in for optimistic rollups. So there has to be a place for me to find how state A went from state A to state B through some transactions. And those transactions have to live somewhere. And if, for example, if the sequencer who are doing this execution go offline, if they're keeping the state or if they're keeping transactions, there has to be an escape hatch. There has to be a data stored somewhere that is not with the sequencer who is executing transactions, but somewhere that you can grab the data and then recalculate all of the state or state transitions to come at the latest state of the L2. Or where do you find your balance? If it stays in the sequencer, if the sequencer goes down today, you don't know how much you have, you don't know your balance. So what you could do is you can still take your data, state data or transaction data, and then this actually should be transaction, and put it on L1. So the problem there is it's very expensive at the moment. You would get the security of your L1, which is, let's say in this case, Ethereum, which is really good. But for some use cases, it might not really be the best choice, right? Proto-dank sharding is trying to solve this, but there's still some way to go there. Let's see. So what are we coming up with right now? We came up with a really lean solution on top of NEAR protocol as a smart contract layer. We created a blob data smart contract where you can just put any data as long as the blob data. We don't really check what kind of data it is. You can just use it as a data layer, data availability layer. We created a light client for inclusion proofs where you can just go and ask, hey, can you check please if this blob contains this data or if my blob is actually included in the chain. And we created a minimal RPC client for Rust and non-Rust interactions. So we have already with Go and Rust. And it's very lean. You can just use it as a HTTP server if you want to use, or you can just put it into your L2 node to interact with the NEAR blockchain. Let's see. How do we store the data? A little bit more in depth. And how do we get actually consensus on the data, right? Because that is what we're trying to do. We're trying to provide some security on the data itself too. When a producer processes a receipt, there is consensus around the receipt. So we don't actually put the data on the state, but we just put it as call data, the same way that Ethereum does it, as an input to the smart contract. And then we keep it for an amount of time. This is configurable. The pruning time for now in the config is at least 3 NEAR epochs, where each epoch is 12 hours. But this is basically something that you can configure if you're going to go higher. If you're going to go lower, it's a different topic. What do we do with the data that we're getting? It's really easy to understand, actually. We take a blob of data, chunk it into 2 56-byte pieces, we Merkleize the whole thing, we get the Merkle root for the commitment, and then we take the transaction ID from NEAR, and then we put the commitment next to it, and then we push it to L1 data. It's just 64 bytes. And then we push the actual blob data, push the blob data directly to NEAR protocol. So the consensus is provided around submission of a blob by NEAR validators, and commitment is available for a long time. Depends how long you want, actually. And the commitment is very straightforward to understand. It's just a Merkle root. How do you verify your blob? You go grab the NEAR transaction ID from Ethereum for the block commitment that you want. You go back to the light client ask for an inclusion proof for the transaction ID. You get the Merkle inclusion proof and ask the light client to verify that inclusion proof for you. So when we look at the diagram of how this would look like, the blue part's what we did. Well, NEAR protocol, not specifically, it's been around for a while, but the new ones are, we created a NEAR DA client. What we do is Ethereum, an L2 rollup basically derives its blocks from an L1. You execute some transactions, and then you post commitments and sequence data to a NEAR DA client that posts it, that creates commitments, puts into NEAR protocol in the contract itself. And then anybody who's a fisherman for optimistic rollups, for example, can go and ask inclusion proofs for the blobs that they want to get inclusion proofs on. And that's pretty much it, actually, from a technical standpoint. It's, again, very easy to understand, right? There's a blob, there's a namespace, which is just any rollup that you want to provide in. You provide the commitment, you provide the data in a blob. The namespace is, it's a version and ID. You can just think about like a chain ID and then the versioning of the chain. Frame reference is transaction ID and commitment. That's what we push to the L1, right? And then we created the DA RPC. We submit the blob into NEAR, and then we submit the commitments into the L1. Sorry about the on top of the headlines. So why build on NEAR DA layer? One of the reasons is very cheap. It's 8,000 times cheaper to post the L2 state on NEAR versus ETH. It's an already bootstrapped network. We've been up since almost nearly 4 years now, I think, with 100% uptime. So the security guarantee is already there. The uptime is already there. We created a really lightweight DA client that you can just push into your L2 node so that you can use directly, and fast finality on state. So this is very exciting for me. What are we going to do next for NEAR DA? We want to, this is not full commitment, just to say, this is very much like a roadmap-y, what we think we're gonna do. It could change anytime, right? We want to do some data availability sampling. Where it's gonna live, is it gonna be on its own node or is it gonna be on the protocol? That is up for discussion. We want to introduce data redundancies on top of NEAR. We're looking into 2D erasure coding, homomorphic hashing, so that the blow-up factor doesn't increase a lot. We want to lower the barrier to entry by DAS, because right now, for you to access the data, you need to run a node, right? Or ask an RPC. We're thinking about room to create some economies around DAS clients. Again, like I said, we now have a light client and we have to ask the light client if the blob is included or not, but we're thinking about maybe implementing KZG commitments. Actually, we have something already in the repo if you guys want to check out. There's a erasure coding, KZG commitment on top of an erasure coding that we're looking into, which will remove the need for light client interaction, so it's going to be non-interactive. Room for optimizations with multi-proofs. We're thinking about sampling individual code words. Something that we're thinking to do to increase the security of the data availability layer. If you want to combine the security of Ethereum with NEAR validators, we're looking into how we can include eigenlayer and make data availability obstruction, I guess, a slashable offense. It was supposed to be a demo. But my computer didn't work. So instead, what I'm going to do is I'm going to take as much questions as you can ask, and that's going to be it. Yeah, questions. Marcin.
Okay. So on one side, the NEAR Lite client verification depends on validator signatures.
Right.
And validators don't get penalized for giving
Yes.
fake signatures for light clients.
Right.
So in theory, they can lie to Ethereum.
They can lie on what exactly, though?
They can claim that a given block was received.
So there's no slashable offense, yes.
Yes,
That's what we're trying
exactly.
to say.
So
that's why we're
any
looking into it, right? That's why currently, you can also not show the data and say like, oh yeah, it's available, and then just go on. That's also the same problem, right? So there has to be slashable offense at the end of the day. Yeah, you're right. I agree. It's an improvement that we're looking into.
And the second question is, like, light clients come with some delay, right? They do not get every block. They get every nth block.
Yeah.
How big is the delay? And does it
I actually don't know. I should probably look into it, but I will.
Because in some scenarios, I remember it could be as large as the whole epoch. Hopefully not, but because
when you ask for the transaction, or what do you want to ask from the light client? The block.
Yeah, kind of, because in theory, in order for L2 to commit the proof, this L1 contract that's committing the proof has to check that it got the light client information from NEAR.
Yes.
Otherwise, it should not kind of accept the proof.
Yes.
Right.
Ah, I see, I see, I see.
And if, for example, NEAR takes, hopefully not, but if NEAR takes, whatever, 8 hours to give this light client information, then the whole thing has to wait.
But the light client asks the network itself, right? So that's what you mean. If there's a delay between the asking, or is there the delay between?
So light client is asking for every single block from NEAR?
No. I'll let Ilya talk.
So because the rotation of validators happens every epoch, right? You just need to catch up on the epoch, on the current validators, and then you can sample any block, and you know the validators of that block. So you don't need to, you just can ask at the time. And then, I mean, there is a slashing for double signing, so they cannot lie on the alternative header. They can lie on the data inclusion, but that would be like invalidating the whole NEAR state transition. No?
Okay, yeah.
For context, Marcin worked on NEAR protocol, so.
So he knows when he's asking a question, actually. But thanks. Any other questions? Yeah.
Can you move to the previous slide? Then show that the fast finality of the fast finality on the state data. How can we have that feature with the data availability? Because usually state data, state lose load up to the layer 1. In this case, Ethereum, right?
Oh, I'm talking about the finality on the data availability on NEAR. I'm not talking about the availability on the L2.
Yeah, so you are talking about the state data.
Well, yes. So what is the question? I didn't get.
Usually, the reason why it takes usually 7 days in the optimistic load-up, we need to wait.
Yeah, but that's the settlement. That's for the settlement, right?
Yes.
So this is not for the settlement. This is for data. Transaction data. This is transaction data. Yeah, exactly. This is not the settlement of the.
Actually, I think it's almost the same because we usually use the state data for securing all the assets in the layer 1.
I think maybe I didn't explain correctly, but this is the data layer, and then settlement goes back onto the L1, right? So the settlement is still 7 days if you want to have to wait for the optimistic case. Okay. So it's not like the withdrawal doesn't really depend on this data.
Okay, got it.
This is transaction data, right?
Okay.
Yeah.
Okay. So the other question is about what is the difference from the if I use the Celestia, NEAR, or Ethereum? What is the difference?
Great question. That is why we're here. So like I explained in a couple of slides. Let me see. Oh yeah, here. Well, one of the reasons so by the way, we're working with all of these. Like we're not, at the end of it, we're trying to push industry forward, right? It's not a zero-sum game. What we're trying to do is what we're trying to claim is that we've been up and running for a long time. And we have proved that our system is very cheap. That is the difference, that is the differentiator from our side.
How about the security?
How about the security?
Yes.
Oh, we have a lot of validators running right now, and they've been running for a while. So you base your security on this. But what kind of security are you looking for?
Actually, when we withdraw our assets in the Ethereum, we need to some kind of proof, and the proof requires some kind of data accessible in the contract that processing all the withdrawals. Your
security model is basically now, if you use this, you're basing your security, data security, transaction security, right, on NEAR protocol validators.
But it's not accessible through the L1 contract that handle withdrawals.
No, right? Because that's the settlement that you're looking for.
Yeah, actually, I attended L2 days yesterday, and there are some arguments about the protecting sharding and the Celestia data layer.
Right.
Yeah, and they are arguing that kind of different level of security among.
Right.
Yeah, yeah.
So you're asking where we stand on that chart of like being in Ethereum versus yeah, okay. That is a good question, I think. And where we lie in terms of security, I don't know where, but it's obviously not as secure as if we don't have enough validators here, right? You're not posting an L1. Between Celestia and what we're doing right now, it's a hard call. There's a lot of factors that I would say to like choose which one's more secure and which one's more and less secure. I cannot give you a definitive answer right now.
Thank you.
If you have time, you have time.
Okay. So, because the one thing I would add is really depends on whether this is optimistic or ZK rollup.
Sure.
Okay, so optimistic, kind of the security of DA is more important, because without this you cannot check the fraud proof, right? For ZK, it's in case the whole L2 disappears, then you cannot recover.
Yeah, basically you depend on Meta Labs sequencers running for a while, right? I mean, that's also fine, right? Like this is all about what you want to do at the end of the day, or how much security you want to have on your system. But you're right, like for optimistic rollup, the DA layer is very important because if it's gone, you cannot provide the fraud proofs. But for ZK, for every execution, you already have the validity proof. It's just the point that if the sequencer disappears, then there's no escape hatch, there's nowhere to go.
And my actual question is, if you look on your Merkleization,
right,
how ZK friendly is this? Or how customizable is this?
How ZK friendly is it? Right now it's not. It's just Merkleization, right? But eventually it will.
No,
do you mean the commitment?
No, the example is that, for example, depending on the hash function that you choose, if you go with Ketchak, it becomes more expensive.
Right. I'm not sure about what exact hash function we use, but it could be, I'm not sure. We have to take a look. But I know what you mean, right? It should be on the repo.
In your in this slide, it says that it's 8,000 times cheaper to post L2 state on NEAR than ETH, which I assume is ETH L1.
Right.
Obviously, it's closer than a Celestia or a XYZ other DA layer. Is there any concern, or I guess, what is the thought process behind using DA layers to bring L2 fees down significantly, and then that is a result, and then how does this affect the sequencer surplus and like of these L2s who are like, for example, Base made a ton of money off Friendtech for that 1 month, or so how do you think these rollups are thinking about DA layers coming in and almost like cutting down their fees or their surplus, or is that happening, or am I missing something?
That is a good question. I think that's a question that we can ask L2s. What I would say is the cheaper that you can get for your own users using your chain, the better for the user experience. And what we're trying to do is increase the usability of these chains in terms of the UX and in terms of basically the fees.
Yeah.
Does that answer your question?
Yeah. And so if posting data to Ethereum L1 now costs 8,000 times more than NEAR DA, that means that any rollup built with NEAR DA in the modular stack, regardless of what the settlement layer is, if it's Ethereum or if it's a different one, is going to be extremely, extremely cheap, like cheaper than anything we've seen.
I don't know how, for example, Celestia costs are.
Right.
But at the end of the day, this is the number that we got after running our
right. But like
basically.
Comparing to Arbitrum or Optimism or insert your L2 here, using NEAR DA or Celestia or any of these DA layers is going to be a significantly cheaper experience. Yes. Yeah, something that like we haven't even.
But it's a trade-off, right? At the end of the day,
yeah.
You're changing your security model basically. There's like DACs here, and then you go up the number of validators, and then the end is basically the L1 itself.
It's just rollups in L1, yeah.
Well, not rollups specifically. Where you settle is where your data is basically the ultimate security that you can have. And then anything in between is like where you want to land in terms of security versus cost.
Yeah. Thanks.
Yeah. Any other
questions yet? Or no?
I see someone.
Yeah, some protocol claim that for fees we don't pay anything to. I mean, no fees, no on transactions.
Right.
Like, is that possible to without paying anything, or it's just
so
a
this
dream?
is not. There might be a misconception. This is not free. This is cheaper.
Okay,
right?
they claim our transaction is free, and then you don't need to pay anything like that. Is that possible, or it just?
Oh, this is a completely different topic. You mean like transaction fees being?
Yeah.
Like especially, let's talk about Near Protocol because I'm part of Near Protocol. It's cheap, right? But as a user, you still have to pay. So we came up with this new technology called meta transactions. I think Ethereum has the same, where you can sponsor other people's transactions. So if you're a user, at the end of the day, you can see your transaction cost as 0, but somebody has to pay. So somebody else sponsors you.
Yeah.
Is that what you're trying to get to?
Yes. I mean, for me, it's meaningless because otherwise the validators.
Sure. I get you. But what I mean is, like at the end of the day, the validators have to get some value so that they validate the data, right? So in my opinion, there has to be someone paying the transactions at the end of the day. It depends who pays for it. Is it the end user? Is it the sponsor? Is it the application? That is something that can be solved on one layer higher.
Okay.
But at the end of the day, somebody has to execute these transactions somewhere to change the state, and then they have to get paid. Otherwise, they're not going to do it. So yeah, I hope that answered your question.
I'm late to the party, but was there a comparison with
No.
Can we get one?
Maybe soon. But Ilya, maybe.
There.
Are you gonna ask?
Yeah, I was frantically looking up the stats for Celestia. I mean, this, like, obviously it just launched, so there's nothing live yet. But they have 2 to 8 megabyte blocks every 11 seconds, and so this is
Okay.
yeah, like less than, I don't know, few, like it's very little, honestly, like for data availability. And then the question of the fees obviously comes, like how full they will be, right? So on Near we have, at least like I'm estimating, I don't know, I was asking Bowen the exact numbers, like 4 megabytes per chunk. And so we have 4 shards, so you can do 16 megabytes per second.
For now.
For now, yeah. And then Q1, the idea is to add more shards. So, and like the cost is the one you see. And so it presumably has a lot more capacity. So you can have pretty much, hundreds of thousands of transactions per second on rollups settling into Near's DA for like 0.1 Near per block, something like that.
Less.
Yeah. So very cheap. As you said, like, yeah, we have not seen these prices yet.
No.
It's going to be fun. Thanks, Firat. Give it up for Firat.